All right, hopefully everything's set. Welcome everyone to Leveraging Big Data with Apache Spark. I'm JP Powers, and I'm a research data scientist in the Trax Data Science Lab. Loosely speaking, this seminar is going to be following up on the seminar I gave back in November, which was an introduction to AI, big data, and cloud computing. So we'll revisit a few concepts that I talked about in that presentation as we go along through this one. And today we're talking about Spark. So we'll cover what it is, who uses it, and then we'll spend the bulk of our time talking about how does it work and how to use it, with just a brief discussion at the end on alternative data solutions. And the one note I want to make before I launch into this is that I'll be presenting Spark from a data scientist's perspective or a user's perspective. I can't speak to it in the way that a Spark developer or a data engineer might be able to. And our lab focuses more on actually using these tools to do data science. But even as users, it's important for us to have a working understanding of our tools. So I've been using Spark for a couple years now, and I'll try to pass on some of what I've learned to you as maybe current or new or potential future users of this. So starting with what is Spark? At this point, we'll just do a quick overview, and then we'll get into more of the details when we talk about the how does Spark work section. But simply, Spark is an open source software product, and it's often referred to as an engine for big data processing. And what it does is really speed up the processing of large amounts of data beyond what was possible before it came around. And it enables this in a few different ways. So first, distributed processing or distributed computing and parallel processing. Second, in-memory computing. And third, various optimizations. So we'll dig into each of these in a bit, but first we'll just quickly review this concept of big data to make sure everyone's on the same page, because it's so central to what we'll be discussing here. So people use the term big data in a couple main ways. One is to think about it at the data set level. But even with this approach, it's not as simple as a size cutoff. It's more this idea that once a data set becomes too large or too complex to be effectively handled with traditional storage, processing, and analysis, then you've entered the territory of big data, and you'll need a different set of tools to work with it. For example, a lot of people rely heavily on Microsoft Excel to handle data, but products like Excel are only designed to handle relatively small amounts and limited types of data. Similarly, many other traditional tools and methods will lose effectiveness when data become too large or complex. And these include our statistical apps, traditional statistical testing, and even code-based tools like pandas. The other way people use the term big data is not in reference to a given data set, but just referring to this general field that encompasses massive data sources and the emerging technologies for dealing with those. But by either use of the term, Spark is designed to be a big data solution. So who uses Spark? According to Spark, thousands of organizations worldwide. So here's a small sample of some of those that I'm presenting here. Spark also specifically reports that 80% of Fortune 500 companies use their product. So it is widespread among the companies and organizations that need to do work with big data. This plot here comes from OSS Insight, which is a web tool that reports analytics on open source software projects using GitHub data. And here it's ranking open source big data software by the number of pull requests per year on GitHub. And according to this summary, Spark has been one of, if not the most widely or most actively developed projects, open source projects in big data over the last 10 years. So we do see a dip into the second place spot at the end on 2025 there, but obviously we don't have all the data for 2025 yet. So overall, Spark is likely the most widely used engine for scalable computing. And on Databricks alone, exabytes of data are processed on a daily basis. So that's after gigabytes, you get to terabytes, then petabytes, and then exabytes. So many bytes. And we'll talk about what Databricks is later, but for now, just know that it's one of the ways to access Spark. And notably, we use Spark in the TDSL. So we've done a lot of work with N3C, which is the National Clinical Cohort Collaborative. It was formerly called the National COVID Cohort Collaborative when they used to focus exclusively on COVID. Since then, they've expanded into some other clinical domains. So this is a project supported by NIH's NCATS, or National Center for Advancing Translational Sciences. And 75 plus institutions have contributed electronic health record data to this large centralized repository. And then users can access and work with the data in these enclaves that are powered by the Palantir Foundry platform, which is a big data platform that uses Spark as its underlying engine. We also use Spark for other local projects that we do using other cloud computing platforms. And these include Azure Databricks and Microsoft Fabric, which we'll touch on again a little later. And Spark may be in your future as well if you're not already using it. There are plans to make Spark available later this year to UNC researchers that are using data from the Carolina Data Warehouse for Health. So this could be something you have access to in the future if you don't at this point. All right, so shifting now to how does Spark work? To answer this, we're going to walk through a little story of where Spark came from, how it became what it is today. And this history will help us to break down how Spark works, because we'll see it's a series of solving problems. Each new development overcomes a previous limitation. So by following this story, we'll see what some of those problems and solutions were. And we'll begin with a couple developments that were published by Google in the early 2000s. So the first of these came out in 2003, and it was this paper about the Google file system. So this was a scalable distributed file system for big data. We'll circle back on this concept of scalability in a little more detail. The distributed part is pretty much what it sounds like. So once you have data that are so large, they can't be stored on some single storage container, you can partition the data and distribute it across several containers on a distributed system. So that was the first one. And then the next year, they came out with this publication on MapReduce. So this was a programming model for processing big data on large clusters. And by this, they mean that you have a cluster of many computers, and you can split up the data processing task across all those computers. So the first paper was a solution for distributed storage, and then the second paper is a solution for distributed processing. And Google was already implementing these technologies in their own products, but through these publications, they were making the underlying insights and methods then publicly available. So around the same time, there were developers at Apache who were trying to create an open source web crawler. And what they found as they got along in the project, they got to the point where they could start to estimate their costs for hardware and computing, what they would need to achieve their goals. They found out it was going to be prohibitively expensive. So the project was at a standstill until those Google publications were released. So once those came out, these developers were able to come up with open source versions of those solutions. And these got rolled into a whole new project called Apache Hadoop. So it became its own project because they realized these technologies could be applied much more broadly than just the web crawler that they were initially working on. So since its inception, Hadoop has come to include many different components, but two of the core ones are the Hadoop distributed file system, which is, of course, akin to that Google file system from that first paper, and then Hadoop MapReduce, similar to the MapReduce programming model from the second publication. So these technologies would form the basis for a general solution for big data processing. So Hadoop running on a cluster of computers was able to outperform supercomputers with respect to processing speed. And this highlights a big key of Hadoop's design, which was about reducing the need for ultra high-end specialty hardware. Instead, you can utilize more of the more standard hardware. And this is referred to as scaling out as opposed to scaling up. And we'll come back to this concept as well. But Hadoop was really a big success. So major companies like Yahoo and Facebook quickly adopted Hadoop to handle their data needs. Hadoop nevertheless had some limitations, as all systems do, and these included accessibility. So it was written in Java, and it wasn't the most easy to use. So this wasn't the sort of product that was going to be accessible to the everyday users. It was more for these specialty teams working at these large companies. And then while speed was really the strength of Hadoop, there were limitations there as well. So the way Hadoop works, it has to read data from and then write data back to storage as it's doing its processing. And just by nature of how that works, that was always going to be a limitation on the speeds that Hadoop could achieve. So this is really when Apache Spark came along as a solution to overcome those limitations. So it was first released open source in 2010, but it was released more independently, and then they came under the umbrella of Apache in 2013. So the big difference with Apache Spark was they were going to try to perform as much computation in memory as possible relative to Hadoop. So cutting down that back and forth between storage and RAM allowed them to achieve speeds up to 100 times faster than Hadoop at the time. And this wasn't true right when Spark first came out, but shortly after, they were able to start making it more accessible by adding support for Python, SQL, and R, so users could interface with those languages. One notable caveat with Spark, though, was it was originally designed for on-premises deployment with local computer clusters. It wasn't designed as a cloud technology. So we'll do a quick refresher on cloud computing here. The basic idea is you're outsourcing your computing work to faraway computers, and then you can access and manage those through the internet. And this is in contrast then with your on-premises traditional computing, where the processing work is done on the computer you're using or the local cluster or local server, essentially local computers. So with cloud computing, you're using this remote computing equipment, which is generally owned and operated by a third party. So that's going to be your cloud provider. The cloud provider specializes in maintaining advanced computing resources. The idea being they specialize in doing this so that they can offer it as a service and you don't have to. So you pay to access their compute resources rather than buying, building, and maintaining your own. And then you can use more resources when you need to, you can use fewer when you need to, and you just pay for what you use. So that's the basic idea for cloud computing. And Spark itself was not originally designed for cloud computing. But in 2013, the creators of Spark formed Databricks. And the name Databricks refers to both the company that they formed. It also refers to their product, which was intended to be a complete cloud-based development environment for doing data science, which was built on Spark. And this was really true from the inception of Databricks, but it's especially true now that Databricks is very much focused around AI applications with big data. So it is a general data science platform, but they really focus their efforts on enabling AI applications, including machine learning. So Spark is an open source project under Apache, as we've said. Databricks is not. It's a commercial cloud platform. And while advancements are continually being made to the open source Spark, some of the latest Spark enhancements are proprietary and they're exclusive only to Databricks. Sometimes these may go on to be released to open source Spark, sometimes not. But the takeaway here is Spark is the open source big data processing engine Databricks is the commercial platform that adds cloud-based data science tools and services on top of Spark to try to offer a more complete solution for doing data science. All right, so here we'll circle back to some of the principles that I mentioned underlying Spark in a little more detail. And we'll start with distributed computing, parallel processing. So here we come back to this idea of scaling up versus scaling out. These are also called vertical scaling versus horizontal scaling. So in some ways, scaling up is the older of these models. The basic idea is when you have greater computing needs, then you're going to get or build a more powerful computer with better processors, more RAM, more storage, etc. So let's say you start with your basic PC, you could then scale up to a gaming PC that has more powerful specs. And from there, you could even scale up to the elite world of the supercomputers with the highest end specs available. Hadoop and Spark, on the other hand, are more based on the scaling out model. So this is where, rather than building a supercomputer, you make a lot of standard computers work together in coordination. And this is oversimplifying a bit, but it is the basic idea. And this is what those initial Google developments were all about. So those were solutions for scaling out. First, for storage, to distribute storage across many machines by chunking data into partitions, and then scaling out processing by distributing that across machines. So you divide up your data processing task into smaller tasks that can then run on separate partitions of your data. And then all of the results have to be combined together at the end. So here's a more visual description of how this works with Spark. So you connect Spark to a cluster of computers or compute processes, and then one of those computers is going to act as the driver node for your cluster. The others will act as the worker nodes. So when you go to run your code in Spark, that will go down to the driver node. The driver node is then responsible for figuring out how that work can be distributed across all of the workers. And it will send out those instructions to the worker nodes. Those will then grab whatever partitions of data they need from your distributed storage. They'll do all of the processing they need to do. And then depending on what your code is actually doing, they might write some result back to distributed storage, or they might send results back up to the driver where they can be aggregated. So that's our distributed computing. And now let's look at in-memory computing. And we've more or less covered this, but again, the defining feature around the creation of Spark as compared to Hadoop was it was going to try to perform as much computation in memory as possible. So in general, computing involves this back and forth where data has to be read from storage, pulled into RAM, it can be processed in RAM, and then things need to be written back to storage. And this goes back and forth because RAM's not meant for long-term data storage. So it's always files have to be written back, temporary files, final files to storage. But accessing data that are already in RAM is much faster than reading the data from storage. And this can result in orders of magnitude speed increases. Of course, there's still some back and forth with storage, but the idea is you hold the data as long as possible in RAM until all computations are complete. The caveat to doing this, of course, is that you do need a lot of RAM to work in this way, but scaled out distributed computing makes this a possibility. And then last, let's talk about some optimizations. So early on in the life of Spark, the developers added the Spark SQL module, and this had a few big impacts. One of them was it created some easier ways for people to use Spark, but it also enabled some major optimizations. And these optimizations leverage the declarative nature of SQL as a programming language. So wrapping your head around the distinction between declarative programming and imperative programming, I find to be more tricky than it seems at first. And it's really beyond our scope here. The gist for our purposes is that declarative programming looks more like describing to the computer the outcome that you want to achieve rather than providing it with the exact steps to get there. And SQL queries are declarative in this way. The result of this is that since you're describing the outcome to Spark rather than the steps it has to take, Spark then has the latitude to come up with the steps that it thinks are going to be the optimal way to get there. And this is such a powerful feature for improving performance in Spark that even if you're writing your Spark code in languages other than SQL, that code is still often getting interpreted to Spark SQL under the hood so that Spark can still leverage these optimizations. So Catalyst and Tungsten are the name of two of the optimization tools in Spark that have been around for a while that help to enable this. Adaptive query execution is the newer tool, a little bit more recently implemented in Spark. And all of these tools together enable this process that looks like the following. So you tell Spark to run your code. Spark evaluates what it is you're trying to do. And then it develops a series of possible plans, runs estimations on those to try to figure out what the optimal plan is. And then it goes ahead and executes that one. And then this is where the newer tool, adaptive query execution, comes in, because now, even while Spark is going ahead and executing that plan, it gathers some analytics while it's working to test its performance, look for ways to further optimize the execution plan, and it will go ahead and implement those optimizations on the fly while it's running. So one of Spark's goals over time has been to shift the responsibility for optimizing performance away from the user. So in the past, if you wanted to squeeze the maximum performance you could out of Spark, it was going to require some manual configuration. But now Spark has optimized so much or automated so much of their optimization. So we're at this point where in most cases, it's not generally considered worth the user's time to tinker with configuration to chase performance gains, because Spark will do a good enough job on its own. All right, so that wraps up our section on how Spark works. Of course, there's a huge world of further detail that you can get into. Much of it is still beyond my knowledge, but we've gone through some of the major concepts that it's helpful for a user to know. Just keep in mind, though, that Spark is releasing new developments all the time, and those do impact how Spark works, sometimes in small ways, sometimes in big ways. All right, so we're on to how to use Spark. So as we've mentioned, Spark can be deployed on premises to a local computing cluster as it was sort of originally designed. Of course, this is going to require some manual configuration, and you have to have an appropriate distributed hardware setup for that. But these days, Spark is also integrated into numerous cloud computing platforms. Of course, chief among those being Databricks, the platform from Spark's creators. Just to keep things confusing, though, if you are using Databricks, you won't be using a product that is just called Databricks. So it gets integrated into some larger cloud provider systems. And these are Microsoft Azure, Amazon Web Services, and Google Cloud Platform. So you would actually be using Azure Databricks, which is what we use, or AWS Databricks or CGP Databricks. But outside of Databricks, Spark is also integrated into other cloud platforms. So these include Microsoft Fabric, which is Microsoft's own cloud data platform, and Palantir Foundry, we've mentioned, is another big data platform, as well as many others. So I haven't seen specific data on this, but I imagine that at this point, Spark is now used far more commonly through these cloud platforms than it is through on-prem deployments. Spark was originally written in Scala, and it still is for the most part, Scala being a derivative of the Java programming language. So when Spark came out, to use it, you had to write code in Scala, and you had to use a data structure called resilient distributed data sets. And people did not like these they're a bit cumbersome and non-intuitive to work with. So Spark pretty quickly worked to build some APIs that allowed users to interact with Spark using more familiar languages and more familiar data structures. So users can now use Python, SQL, and R to write their code for Spark. And you can use a data structure called data frames, which are similar to the data frames in Python and R, and somewhat similar to SQL tables. So on the previous slide, we looked at the various platforms people can use to work with Spark. And this figure just refers to using Spark through Databricks. But Databricks released these data in 2020, analyzing what their users use when they create code notebooks in Databricks. And so they're saying that 69% of code written in Databricks notebooks is in Python, 18% in SQL, 11% in Scala, and 2% in R. So they've seen that Python is the most popular language among their users, and this has created a feedback loop where the majority of users they know want to use Python, and Python has good support for data science and AI. So the developers especially focus on facilitating Python in Spark and Databricks. This encourages greater user preference for it and so on. So the result is that currently and for the foreseeable future, Python is the language that enables the maximum functionality in Databricks. So what does it look like to use Python, for example, with Spark? In order to use Spark in Python, you use the PySpark library. This is the Python API for Spark. In other words, it provides tools in Python for accessing Spark objects and functionality. And most of the functions that you'll use in your code would specifically come from the PySpark SQL module, which is a module of the PySpark library. I know it gets confusing because SQL is in the name, but you're working in Python, and it really is just confusing. So the reason you have to use this PySpark code is because you're interacting with these data frames, which are a distributed data structure. So in order to handle those, it needs to use some special code under the hood. That's why you have to go through PySpark. But other than the functions you're doing in PySpark, you're still using regular Python syntax. So if you write a for loop, it still looks the same as writing a for loop in Python normally. All right, we've gotten to this point where I'm going to have a little dance with Zoom. And if everything is still up and running the way it's supposed to be, we'll walk through a simple demonstration of what this can look like. Oh, Zoom can see it. You cannot see it in the room. Okay, I'll just have to look at the screen. All right, so here we are in Azure Databricks. So this is a code notebook in Databricks, and in these notebooks, you can set what you want the main language to be. So up here, you can see I've set it to be Python. And then this green dot over here and this gibberish underneath it is saying that our notebook is connected to a compute cluster already. So when we connect the notebook to a compute cluster, a Spark session is automatically started up and we get connected to it. So we're ready to write code in the notebook now that will utilize Spark on this cluster. All right, so first off, we're just going to do some basic code imports. We're pulling in some regular Python stuff, some plotting, but then also these PySpark SQL functions. And then once that finishes up, we'll go ahead with this next cell, which is not terribly important. We're going to be pulling in a couple data sets here. And so as not to show you the full file paths to those data sets, they're stored in an external JSON file. So I'm just pulling in that JSON file here. And then, like I said, we're already connected to a Spark session. So we can see here that, is this big enough for you all to read in the room? Ish. Okay. We can see here that we have this object called Spark in our environment, and it's of type class PySpark SQL session Spark session. So that's our Spark session. And we can query attributes about it. So we can see its version, for example, we're using Spark 3.5.0. All right, so to get into the demo portion here, we're going to take a look at some neighborhood level race data that are publicly available from the US Census Bureau. So we're not dealing with any sensitive data here. And to pull this in, we're going to use this PySpark function, spark.read here. So I have these data in a CSV file, and we're going to read that into a Spark data frame and call that race. Normally, you would have the file path back here at the end. I just have this variable in place of that at the moment. And as a side note, CSV files are not a very efficient storage format to use with Spark, but this file is not very big, so it doesn't matter that much in this case. So I'm printing out the rows here, and we can see we have just over 500,000 rows in this data frame now. And it doesn't look like much unless you're really familiar with census data tables, but we're going to clean this up a little bit. So first thing we'll do is use this where method on data frames. We can use that to filter it. So we'll filter on the first column, which was GeoID, and we're going to use that to filter down from this data is currently all the United States. We're going to filter it down to just data on neighborhoods in North Carolina. So that's what that first part will do. And then we'll use the with column method on the data frame. Normally you use with column to add a new column to your data frame, but you can also use it to overwrite a current column if you want to make some adjustment to it. And that's what we're doing here. The specific adjustment is not terribly interesting though. So the main result is we can see we filtered down from 500,000 records down to just 2,000 of these neighborhoods now. We'll use a couple more methods. So the select method will go from all of those columns down to just the columns we want to work with here, but they still have gibberish names. So we can use the method with columns renamed, pass it just a regular Python dictionary with more descriptive names for our columns. So one of them will have the total population for the neighborhood, and another one will have the Black or African American population for the neighborhood. Then we'll use the with column method one more time, this time actually adding a new column. So we're creating a column called Black% and doing a little computation so that that will show us the percentage of the population in each neighborhood that's Black or African American. So we'll get that running, and then we have a data frame now that's a little bit more readable. We see our total population for each Black or African American population, and that expressed as a percentage. Now, what we're going to do with this is look at the relationship between the percentage of Black or African American in each neighborhood, and I have these neighborhood deprivation scores, and I have these stored in another data set here. So similar to before, we'll use that spark.read to read in the CSV with these neighborhood scores, and then the select method to just pull out the specific columns we want from it. And then in the next cell, we'll do an inner join between our two data sets now, a very common SQL operation. And we're joining them based on the column that the two data sets have in common, which is GeoID. And once we do that, we see we still have our 2,000 neighborhoods. We have all the same data from before, but now we've added on this new column at the end, which are the neighborhood deprivation scores. So at this point, we're ready to go ahead and plot to see what this relationship looks like. In our case, the data set we have at this point is small enough that we're just going to convert it to a regular pandas data frame, because these Python plotting functions don't know how to handle a Spark data frame. So ours is small enough, we can just use the toPandas method to make it a regular pandas data frame. If you still had really big data at this point, you might downsample it to get something for plotting. There are other solutions too, but we're not going to get into those here. All right, so then we can see here that as we go from the lowest deprivation scores up to the highest, in these neighborhoods with the lowest scores, they also have very low percentages of Black population. It stabilizes a little bit over the mid-range of the scores, but then when you get to the neighborhoods that have the highest deprivation scores, we see the percentage of Black or African American population start to rise. All right, the last thing I want to demo here is just how we could incorporate SQL into this notebook if we want to. So in order to make this data frame we have at this point, to make those data available to SQL code, we have to kind of convert it into a form that SQL knows how to look at. And to do that, we have a method on data frame called create or replace temp view, which is a very SQL sounding name. So it's going to create a temporary view out of our data frame that's called data view. And then once it's there, we can interact with it with SQL code. And there's a couple ways we can do that. So the first way I'm showing here is if we want to stay more in our Python context, we can use this PySpark function, spark.sql, and then we pass it a long string that just contains our SQL query. And what it will do then is Spark will run the SQL query and return the results as a Spark data frame, which we're calling summary1 here. And all I've asked it to do here are count the neighborhoods and compute the average of the Black percent column. The other approach we could take here is in Databricks, we could use what are called magic commands. So that's what I'm doing at the top of the cell here with this percent SQL. So this tells Spark, when you read this code cell, don't interpret it using the Python API, interpret it using the Spark SQL API. So in this way, we can just run the SQL code directly at that point, and we get the same result. All right, so that's exciting demo time done. Let me get resituated. Peter, we got it? Yes. Okay. All right, back to slides. All right, to wrap up our discussion on using Spark, I want to briefly highlight a few things we know about where Spark is headed. So two of their major priorities are on improving the ease of use of Spark and how it can integrate with other software. So more specifically, Spark wants to make it easier for the user to get the optimal performance out of Spark so that users can just focus on creating code. Spark will take care of all of the performance side. Spark has been very focused on interoperability lately as well. So they're working to create a lot of new ways for Spark to connect to the other tools that their users are using. It seems clear also that Python will continue to be a focal point for Spark and Databricks in terms of languages. Photon is a major development that they've been working on. Currently, it's only available through Databricks, but it may eventually be rolled out into open source Spark. So Photon is a complete rebuilding from the ground up of the Spark core engine in C++, whereas before it was in Scala. The idea is that they can ultimately make it more performant in C++ than they could in Scala. And they're advertising 3 to 8 times speed increases on average. But I think these numbers could potentially continue to go up in the future because this is an ongoing project and they haven't finished this rebuild yet. And just one other interesting development I want to mention here. So some people that are fully on board the LLM train have been presenting this idea of coding in English. In other words, if we sufficiently integrate LLMs into a coding environment, people could just write their so-called code in English, and the LLM could translate their prompts into the needed programming language. And Spark has taken a stab at this, and they call this their English SDK for Apache Spark. So from what I've seen of it, it looks like a beta version right now. I'm not sure whether it's really going to gain traction and be further developed into a full-blown sort of feature, or if it will just end up being a fun gimmick, but it did make for a splashy demo at their most recent annual conference. All right, and finally, we'll have a little discussion on these alternative data solutions. This is a little bit of an aside, but I think it's relevant to some people in our audience. So within Databricks specifically, Spark was originally working with data lakes, which are a very flexible approach to distributed storage. You can think of a data lake like a giant hard drive. You can really throw whatever data you want on there. And data lakes are great for flexibility, but they are so lacking in any enforced structure that they can get chaotic and confusing, especially if it's being shared across many different teams at a large organization. So eventually, this resulted in a push in the big data community to reintroduce more relational database functionality back into some of these big data platforms. The response from Databricks was to pioneer the data lake house, a cross between a data lake and a data warehouse, which is a more structured data storage approach from the SQL and relational database world. So what they did for this was develop a tool stack that can sit on the data lake and give it some of the relational database or warehouse functionality. And this concept of a data lake house has gained a lot of popularity. Meanwhile, though, some other products have been coming from the opposite direction, where they're starting with a data warehouse model and then scaling it out to support big data. So these include products like Snowflake, Amazon Redshift, Google BigQuery, and Azure Synapse Analytics, which used to be called Azure SQL Data Warehouse. So Databricks is fully invested in this lake house model now. These other products are still working for more of the data warehouse model. I think they're all trying to broaden their scope, though, to cover the most use cases they can, to the point where they're now overlapping. So there can still be important differences between these products, but their features keep evolving, meaning that if one of these products didn't support your use case in the past, it might now. And if it doesn't now, they're probably working on it. So it's a quickly changing landscape, but just be aware that there are various options out there for big data systems. All right, so let's summarize some key takeaways. Spark leverages distributed computing, in-memory computing, and optimizations to be an open source engine for big data processing that's used very widely in the world of big data. Spark is available in cloud data platforms, such as their own platform of Databricks. And you can use Spark with Python, SQL, and R. And Apache Spark is actively being developed to make it more performant and easier to use. But keep in mind that there are some proprietary developments to Spark that are only available through Databricks. Also, Spark puts a lot of effort into supporting Python, especially due to its capabilities and popularity with their users. So if you were looking for the optimal Spark setup, in a very general sense, it's going to be using Spark with Python on Databricks. But that being said, Spark is supported on many different big data platforms, and it offers a wide variety of options for both languages and connections to other tools. So I'll stop there. Thank you for your attention, and we can open up to any questions.
People on the Zoom have questions. If they raise their hands, you can facilitate them speaking, or they can.
Yeah, so for our Zoom attendees, if you have questions, you can drop them in the chat, or you can use the raise hand feature and somebody can try to unmute you.
So while that is, people are considering on the Zoom if they have questions, you focused on the Python implementation and usage. Maybe so it's just documented, could you speak a little bit to like the PySpark equivalent for R programmers working in Databricks?
Yes.
Spark?
So question was about, you didn't have your microphone on, did you? Question was about the R equivalent for PySpark if you wanted to use R with Spark. So yes, R does have their equivalents. So the Spark developers themselves worked on a library called Spark R, but the broader R community also developed their own library, which was the Sparkly R library. And I believe Sparkly R was more popular. So at this point, the Spark developers are not planning to continue support for Spark R any further. They're just going to go ahead with the community developed Sparkly R library. So yeah, if you want to access Spark objects and functionalities using R, then you'll use the Sparkly R library to do that. Yeah.
And two non-technical questions. One being, how does processing data in Spark slash Databricks on Spark interact with privacy data protection laws potentially specific to like the kind of work that the data science lab does here or with the data warehouse? And my second question is, if you had to, as a broke student, what's the cheapest way for someone to, what can you comment on the cost and whether there are expensive good alternatives slash most cost effective way of setting this Spark environment?
Yeah, so first question was about data security when you're using Spark. And to be honest, that's not something I think that our lab really has a lot of expertise in. The way that we are using Spark, like I said, they get connected to these larger cloud ecosystems. In our case, we're connected to Microsoft Azure. So our distributed storage is also through Microsoft Azure through their Azure Data Lake storage system. So when we're using Spark in Azure Databricks, our code is living in that Microsoft Azure environment. Our data are living in the Azure cloud environment as well. So everything we're doing is sort of staying up in the Microsoft cloud environment. I can't speak to a lot of detail beyond that, but what I can say is that Azure enables a mind-boggling amount of custom configuration with their products. So I'm sure there are a lot of network settings that could be adjusted to help control some of that in more fine-grained detail, but we're just not too well versed in those details. And the second question was about what's maybe the most affordable way to achieve a setup to get going with Spark. And honestly, there's probably not a very affordable way to do it. So the main way you're probably going to end up interacting with Spark is through a larger organization that has some sort of cloud setup available for it. Spark itself is, again, open source. It doesn't actually cost anything. So you can use Spark for free, but if you want to actually leverage its power, you need hardware that can do that. So if you have the hardware already, then yes, you can implement Spark for free in a more manual configuration. They also have this standalone mode in Spark where if you know that you're going to be connecting to a real Spark cluster at some point, but you just want to work on your Spark code in the meantime, you can kind of trick it into thinking that, your own computer is just the whole cluster and it won't really do much, but you can go ahead and work on your code when you're not connected to the real cluster. But yeah, you kind of have to either have a hardware setup ready to leverage Spark, or you're probably going to be connected to an organization that has a platform integration already set up, which is sort of where we're going with these new platforms for the Carolina Data Warehouse that are hopefully going to be coming online later this year which would give more people in the UNC health informatics community access to Spark. Did we have somebody? Okay.
I'm familiar with Spark through M3C, but I've only used it in that environment. So I'm never quite sure where Spark ends and Foundry begins. But it's occurring to me through your presentation that this is much more Spark is much more popular in the kind of work that we do than I realized. Are there people who publish like Spark-based packages and so if I like invented some new method that, made use of distributed computing in Spark and I wanted to share it? Is that a common thing? So I thought about it, but I was like, who's gonna care? Nobody uses Foundry.
I mean, I have a perspective. I mean, it's a small.
Can you turn on your mic?
But then it's gonna affect.
I can mute mine.
Okay. Let's say. Okay. Well, maybe we're still tuning the audio.
I guess my laptop's connected to the speakers. I didn't know that.
Yeah.
Why don't you come up here?
So I mean, there are a couple of things. So the generally I feel like the Spark community is still relatively small compared to like the entire, say, Python community, or probably even maybe the R community. But there are people that, outside of, say, like the Apache SDK sort of community, do develop particularly like analytic and machine learning focused repos for Spark specifically. So, like one thing that JP was talking about is PySpark is really focused, I would say, on data processing. There's like a lot of support for things that I would almost call like closer to the ETL kind of side of things. It's a lot less robust. PySpark is a lot less robust, I would say, for like analysis than pure Python is. And same thing with visualization. Like there is very little visualization that you can do natively within PySpark, which at times is hard because you're trading off between these data structures. Like I have a gigantic PySpark data frame, but I can't necessarily do analysis with it, or I can't visualize it. Unless I bring it, I coalesce it into Python. But that's hard because like I can only support a Python data frame of a certain size or a pandas data frame of a certain size. So for instance, I was looking at a repo on GitHub that someone had developed purely to try and force basically like the ggplot2 R syntax for visualization into PySpark. So you could take like a PySpark or a Spark data frame, and then you could visualize it natively in Spark using ggplot syntax. Now, the problem is, or at least 2 years ago when I was looking at this, is the communities are small, the user groups are small. And so, there were maybe like 200 people that were actively interested in looking at that. And so if it's buggy, like it's not necessarily robust the way like a big Python or, standard R package would be. But there are definitely people, and I would suspect that that's like a growing ecosystem and people getting more and more involved in it because, I mean, as JP pointed out, like Spark is a gigantic community, especially across not just academia, but like especially the private sector. I think part of the challenge you see though is, for a lot of us, it's sort of like we do one big sort of Apache Spark implementation, right? Like we access Apache Spark as an entire group through an institutional environment, with Microsoft. But if you're like Meta, you have like 200 different Apache Spark installations across all of your different teams, and a lot of people developing locally within those that probably have great packages, but you don't necessarily see the cool stuff that they're developing. So I think that's one of the things that my sense is sort of happening, within the larger Spark community.
A little bit about the Spark thing, the R aspect of that. So for R, one of the big differences between Spark R and Sparkly R, is that Sparkly R was kind of built from the ground up to take, really sort of take that interface that existed with R for data frames, and make the Spark data frames basically comply with that. So when you were using Spark R, you pretty much had to use Spark R functions on it. Whereas with Sparkly R, you can just pipe your Spark data frame directly into ggplot. So Sparkly R was, since it was built by people who knew a lot about R, it was designed for that much more compatibility. And if you look on CRAN, you will see some sort of specialized packages that depend on the Sparkly R package directly, but you can use quite a few things in the normal R ecosystem directly on the Sparkly R data frames. And that's really the big advantage of Sparkly R over Spark R, and changing Spark R to do that would have required probably a ground level refactor. So I can see why they would stop supporting it. So
I don't have anything really further to add on that. Yeah.
To your point, the Sparks ML lib is worth checking out for machine learning applications that are built on Spark.
Yeah.
say, maybe do you just want to give a plug for the research enclave and talk about to the people on top of it? Spark background?
Well, I can reiterate that we're working on a project here in Trax in association with the larger School of Medicine and UNC Health to try to create a better environment for researchers using Carolina Data Warehouse for health data to interact with and analyze those data. And this new secure environment that's being built to do this is planned to include Azure Databricks at this point. So users who have an approved project with funding and IRB approval and can get access to this new system would have access to this environment where they could use Azure Databricks, which would give them access to Spark, looking like what I showed during the demonstration here today. It's planned for later this year, but we're still early enough in the development process that I don't want to make hard promises.
So one note, you did say stick things in the chat window, but you can't because chat's been disabled. I assume you've since noted that. Will Longleaf be included in that Spark cluster, or it'll be purely Azure?
I don't believe that there are plans to integrate with Longleaf at this point. So no, I don't think that's planned to be part of this new environment at this point.
Thank you, and thank you for repeating questions.
All right, thank you, everyone. We'll wrap it up.